In this video, we will explain how to solve kinematics problems using calculus. Now, this requires some basic principles of motion. We will base our discussion today on two very important equations. The first is the fact that instantaneous velocity is an integral of acceleration with respect to time. The second is the instantaneous position is the integral of velocity with respect to time. Now, kinematics is basically about motion of an object from some initial point to a final point with a constant acceleration or constant deceleration. If it's an acceleration, which means the object is speeding up, or if it's deceleration, the object is slowing down. So in this example, the direction of motion is to the right from initial point to the final point. Important parameters or variables of kinematics are the velocity of the object when it was at the initial point, u, the velocity of the object when it gets to the final point, let's call that v, the acceleration of the object, let it be positive or negative, the initial coordinate of the object, let's call it x0, and the coordinate of the object as it gets to the final point. A more crucial parameter is the distance between these 2 points, which we can label as delta x. So it's defined as xt minus x0. So the distance between the initial and the final point. So these are the variables of kinematics. Let's go ahead and get the first equation. So we shall start with the fact that velocity is the integral of acceleration as a function of time. Now we know that for kinematics, acceleration is a constant. Let's call that a. Now this a can be taken out of the integral sign because it's just a constant. So you get a dt. By integrating this, you simply get at plus an integration constant u. Now immediately you can see u is the value of the velocity at t equals to 0 seconds. So u is the initial velocity of this object. So now the complete equation, the first equation of kinematics, can be written in a following manner. So u plus at. So we have the first equation of kinematics. Let's look at the second equation. The second equation can be obtained by using the definition that relates the position of the object at any time t as an integral of velocity with respect to time t. Now we have already found this velocity function in a previous discussion, a previous slide, which is quite simply u plus at. So if we substitute this function inside this integral, you get u plus at dt. Now keep in mind that this u is a constant, this a is a constant, so you can take those two out of the integral sign and it will give you two integrals, t dt, which can be easily integrated to get ut plus half a t squared plus an integration constant, let's call it x0. Now we can immediately see that x0 is just the value of the coordinate at time 0 seconds. So this is the second equation of kinematics. Now we can rearrange this equation more efficiently in terms of distance traveled. Remember the delta x that we talked about in the previous slide, which is xt minus x0, and that is just ut plus half a t squared. So this is the second equation of kinematics, right there. Equation 3. Equation 3 can be obtained by combining the first two equations that we wrote down, v equals u plus at, and delta x equals half at squared plus ut. Now, from the first equation, we can rewrite your time in terms of the other variables, v minus u over a, and substitute this t inside that second equation. So the result that you will get is delta x equals half a v minus u over a squared plus u v minus u over a. So you see that there is no t in this equation. Now when you do this algebra, when you simplify it, what you're going to get is the following. Certain terms will cancel, and this is what you're going to get. So if you rearrange this, you get 2a delta x equals v squared minus u squared. Now this is the third equation of kinematics. The fourth equation is for the average velocity that can be written as the difference in the position x at time t minus the initial position over the time interval between these 2 points. Now, the numerator can be simply written as delta x because that's what it is. It's delta x over t. But we do know delta x from the second equation can be written as half at squared plus ut. So if you substitute this in here, we get the average velocity to be quite simply half at plus u, because the t from the denominator will cancel the t's from the top. But we also know that at is quite simply v minus u. This is from the first equation of kinematics. So the substitution of that will give you v minus u plus u, which is half the final velocity plus the initial velocity equals to v average. So that is the fourth equation of kinematics. Let's do this example from basic principles using calculus. So you have a car passes a signpost at x equals to 0. It has an acceleration of 4 meters per second squared. There should be a squared there because that is the unit of acceleration. At time t equals to 0, the car is at x equals to 5, and the velocity is 15. So that is the initial conditions. Now find the velocity and position at time t equals to 2 seconds. We'll start by writing the velocity function as an integral of the acceleration, a dt. Now we know the acceleration is 4. It is a constant. You can take that out of the integral sign, so it becomes 4 integral of dt, which is 4t plus an integration constant. Now we know that this integration constant is the value of the velocity at t equals to 0, and that is given to be 15 meters per second. So we have a complete equation then for the velocity. So vt equals 4t plus 15. So we can proceed to determine the velocity at t equals to 2. So that is quite simply v at 2 seconds, which is 4 times 2 plus 15, 23 meters per second. So that is the answer to the question of what is the velocity at t equals to 2 seconds. Now what about position? To get the position, you need to proceed to do the integral of vt dt from the definition. Now we already know what vt is. It is 4t plus 15, so dt. So that integral will give you 4 over 2t squared plus 15t plus an integration constant, which we know to be the value of x at t equals to 0, and that is also given, which is 5 meters. So your xt is 2t squared plus 15t plus 5. So that is a plus there. And this is the equation that would enable you to find the position at t equals to 2. So at x at t equals to 2 will be 2 times 2 squared plus 15 2 plus 5. So this is 8, this is 30, this is 5, which is 38 meters. Position at t equals to 2 seconds. Now part B, where is the car located at when the velocity is 25 meters per second? So first we need to find the time for which the velocity is 25 meters per second. So that can be determined by using the first equation here. So you see that you get 5 over 2 seconds for the time when the velocity is 25 meters per second. All you have to do now is to substitute this time inside the expression for the x, the position, and that's going to give you the following, which is 55 meters. So that's the position when the car is moving with a velocity of 25 meters per second. So a piece of rock falls vertically from rest and hit the ground with a speed of 20 meters per second. So from some height, let's call this height h, and the rock is falling from rest. So that means the initial speed is 0 meters per second. When it hits the ground, the speed is 20 meters per second. So that is the final speed. And we want to determine the time it takes to go from the top to the bottom, and also the value of h. So let's start with the velocity. So velocity is the integral of acceleration with respect to time. Now, the acceleration is heading downward with a unit with a magnitude of 9.81 meters per second squared. Now, if you take the y-axis to be upward, then the acceleration is minus 9.81. So the upward direction is plus, the downward direction is negative. So the integral will simply becomes minus 9.81 integral of dt, which is minus 9.81 t plus an integration constant. Now this integration constant is the value of v at t equals to 0, namely the velocity when the motion began, and we know it is 0 meters per second. So that means the complete expression for instantaneous velocity is minus 9.81 t. So to answer the question, how long did it take to fall to the ground from the height it was dropped, meaning what is the time t when the speed is 20 meters per second downward. So all we have to do is to substitute minus 20, minus because the direction of motion is downward, and equate that to minus 9.81 t and solve for the t. And t is 2.04 seconds. So that's the answer for part A. Calculate the height from which it fell, namely the value of h. So to do that, you have to figure out the position with respect to time, and that can be determined by doing the integral of that velocity with respect to time. So we know it's minus 9.81 t dt. After integration, it becomes minus 4.905 t squared plus an integration constant. Let's call it x naught. Since x naught is the value of x at t equals to 0, and that's just h, the expression for the coordinate as a function of time is simply that. So as it hits the ground here, the coordinate at t 2.04 seconds is 0, and putting this inside this equation gives h as 20.4 meters, and that is the answer for part B. As you can see, this method, which is based on basic principles of motion, is very efficient in solving kinematics problems, which also requires minimal memorization of equations.